Hello everyone! So today I thought I'd do something fun and share with you one of my early projects when I was a PhD student at Stanford. This ultimately became one of multiple projects that ended up in my final PhD thesis. And even if you're not super technical, I still think this can be comprehensive and interesting for you. And don't worry if you don't understand all the details, you can still appreciate the story. So I'm going to share some slides. These are slides that I've shown at conferences, job talks, and even my PhD oral defense. And so without further ado, here it is. So the title of this project is going to be called Low Power Gallium Nitride Q-Spoiling for MRI Receive Coil Arrays. And I'm going to explain the meaning of each of these terms as we go on. But to start off, I'm going to give you a brief introduction on MRI for those of you who are unfamiliar. So some of you may have had an MRI scan done before. What happens is you walk into a patient room. They make sure that there's no metal on you because it would interfere with the scan. Likely you're going to change into scrubs. And after that, they're going to walk you in to the magnet room where the magnet sits. And you're going to lie onto the bed and they will push you into the MRI bore. Okay? And usually a scan will take 30 minutes to an hour, so you'll have to lie there for that length of time. And you're going to hear a lot of knocking sounds like, and those are usually those are actually the gradients, which I'll explain later on. And you'll find that a lot of the research that is done in MRI is to make MRI faster. Okay? Now, MRIs are really great for looking at soft tissue contrast, specifically the brain, the heart, ligaments, as opposed to X-ray, which is better for looking at bone. But one of the nice advantages of MRI is very safe. X-ray uses ionizing radiation, which can be linked to cancer. On the other hand, MRI does not rely on ionizing radiation and instead relies on magnetic fields in order to work. So this is a picture of what an MRI bore looks like, just kind of cartoon picture. And it consists of a B0 static field. So in clinics, it's usually 1.5 Tesla or 3 Tesla. This is a magnetic field that is stronger than anything that you will find in nature on this planet. Okay. Secondly, you have what we call a B1 radio frequency RF field. And this is a changing magnetic field that is perpendicular to the B0 field. And it's much weaker in magnitude, usually in the tens of microtesla. And thirdly, we have what we call gradient fields, usually in different directions, X, Y, and Z. And gradient fields are magnetic fields that vary as a function of space. And gradient fields are what gives you spatial selectivity in the image. Because it's a magnetic field that varies in space, it allows you to distinguish like what's on the right side of the body versus the left side. And so the three different types of fields here, the B0, B1, and your gradient fields, they each play different waveforms. And they play out what we call a pulse sequence. So you can think of each of these fields as instruments in a symphony, and the pulse sequence itself is the symphony. And a lot of research has been done to figure out how to optimize a pulse sequence in order to create the best image possible depending on what anatomy you're trying to image. Okay? So here's a picture of a person, okay? And in order for MRI to work, it relies on the existence of proton spins because that's the source of the signal. And our body is largely comprised of water, okay? H2O. And what is H2O comprised of? Hydrogen. Specifically hydrogen proton spins. And that is necessary in order for MRI to work. Once we lie in a scanner in the B0 static field, these proton spins in your body will process at what we call a Larmor frequency that is proportional to the strength of the B0 static field. Okay, and in clinical scanners, usually it's either 1.5 Tesla or 3 Tesla in terms of the magnetic field strength. And 1.5 Tesla corresponds to a Larmor frequency of 63.88 megahertz, while 3 Tesla corresponds to a Larmor frequency of 127.7 megahertz. And so while you're lying in a scanner, the proton spins inside your body are processing at this Larmor frequency. And these proton spins will basically align with the B0 static field and add up to what we call a net magnetization vector M that is parallel with your B0 static field, drawn in this picture. And this magnetization M is going to be the source of your MRI signal. Okay? And what happens is, while you're lying there, there is a B1 RF field that I mentioned earlier that will be applied, and it is applied perpendicular to the direction of your B0 field. When this happens, the proton spins inside your body are excited, tilting that magnetization vector M. Okay, this is called transmit mode. Now, in the next step, your B1 field is turned off, and the MRI scanner will go into what we call receive mode. And during this step, the magnetization vector will relax, your spins will relax, releasing what we call a free induction decay signal, or FID. And this FID signal can be picked up by an MRI receive coil. And that is the source of your MRI signal. And this is all necessary for MRI to work. This is a picture of an MRI receive coil. It can be as simple as a loop with capacitors that we can tune to adjust the resonance frequency. And even though this is a very simple looking receive coil, it's very effective because it has very high SNR. And eventually, Romer, in his landmark paper on phased array, realized that he could take multiple coils and overlap them in order to decouple them. And this would allow for high SNR with a good field of view. And the magic of having multiple coils is now you can pick up signals from each of these coils and then recombine them to create an image with very good SNR. And this sort of paved the way for an important field, which is parallel imaging. See, as I mentioned earlier, MRI can take a long time, and a lot of the research has been put into making it faster. Parallel imaging is a field that has allowed a huge increase in speed, because by having an excess of SNR from parallel imaging, you can trade off some of this SNR for faster scan times. And so, not just in hardware, there have also been developments in algorithms for parallel imaging, such as SENSE, SMASH, compressed sensing, and people have looked at even machine learning and deep learning in order to improve image reconstruction times for MRI applications. So pictured here is a flexible 32-channel coil array. And the first thing you might notice are the cables. There's usually one cable per element. And circle in yellow are the balunds. And these balunds are RF chokes that serve to eliminate the common mode antenna currents that could be traveling on the outer surface of the coaxial shield. Having a lot of cables can be a huge issue because the cables can couple, leading to signal degradation. On top of that, the balunds tend to heat up, which can be an issue for patient safety. And by having lots of cables, it also makes the coil array very difficult to wield, especially for technicians and doctors. And in this picture, we only see a 32-channel array. There have been some coil arrays that have been built with as many as 128 elements. And so the moral of the story here is we would like to eliminate the cables if we can. And so this has motivated a lot of researchers to look into making lightweight wearable and wireless array coils. And today's project is one of many projects that we worked on in order to achieve the dream of wireless array coils. Now, having a fully autonomous battery or wireless powered system would require a lower power receive chain, since the electronics will be on coil. And at the same time, we have to worry about patient safety. And here we get to the topic of the project, which is we found that the coil decoupling process, also known as Q-spoiling, and also a process that's necessary for safety, is a huge opportunity for us to save power. And so in this talk, I'm going to explain to you what we did in order to improve power savings in the Q-spoiling process for MRI that would eventually be useful for wireless receive array coils. Okay, so back to our cartoon MRI bore. What is Q-spoiling exactly? Well, during transmit mode, your B1 field is turned on, and usually if you had a MRI receive coil, that B1 could induce high currents through the coil that can be an issue for patient safety as well as the protection of electronics in your receive chain, such as the low noise amplifier. But instead, the receive coil will undergo a Q-spoiling process in which the coil is decoupled and you're able to block high currents from being induced in this loop. And this only happens during transmit mode. Once the scanner switches into receive mode, Q-spoiling would be turned off, and the coil can detect signal as normal and pick up the free induction decay signal that is being emitted from the body. So to the right is a picture of a MRI receive coil, and it is as simple as I described it earlier. It's just a loop with capacitors in between that can be used to adjust its resonance frequency. Now, a Q-spoiling circuit is as simple as having a capacitor, an inductor, and conventionally with a pin diode. And I'll explain how it works later. So here's a picture of a Q-spoil tank again. During receive mode, there is no bias current being applied, and the pin diode is off. And imagine the coil is to the right of this circuit. When the pin diode is off, the coil will be able to receive a signal as per usual. Now, when Q-spoiling is activated, the scanner would apply a 100 milliamp bias current. And this would turn on the pin diode and create an LC resonance tank that provides a high impedance specifically at omega naught equals 1 over square root of LC. And you would tune this Q-spoiling circuit to coincide with the Larmor frequency of the proton spins. It turns out that instead of using a pin diode, which consumes 100 milliamps of current, you can actually replace it with a FET device. And a FET device can allow you to save on this current. And in this picture, if the FET switch is turned on, you can activate your LC resonant tank as usual. So easily you can see that there is potential for power savings. And if you had only one coil, you might say, well, it's just 100 milliamps, like who cares? But if we were to go into an array of coils, for instance, 32 channel arrays, we can save over 3 amps of current. So from looking at this, we see that it is possible to have significant power savings in Q-spoiling by using FET-based Q-spoiling methods. And so that is the essence of this project. So first of all, let's talk about the figure of merit that we're going to use to evaluate the FET devices. Now, we're using depletion mode devices, which means that if we apply 0 volts to the gate, you can model the FET as an on resistance. And if you apply a negative voltage bias to the gate, the device is off, and you can model it as an off capacitance. The figure of merit that we are going to use in evaluating the FET is the R on C off product. And the lower the figure of merit, the better it is for us. So we started looking into Cree's gallium nitride depletion mode HEMT devices. In the past, people have looked into enhancement mode gallium nitride FET devices, and these were largely ineffective because they had very large off capacitance, which you have to resonate out with additional inductor. It can be an issue as we get into higher fields and higher frequencies. And so with the new Cree gallium nitride depletion mode HEMT parts that we were looking at, we had two very nice features. The first is, because it's a depletion mode device, it Q-spoils when it's unpowered, which is very good for safety reasons. The second reason that these gallium nitride devices are great is there is a much smaller drain to source off capacitance. And so this simplifies the circuit that we're building. And we'll show later on that it has a very good R on C off product. So here is, again, a general picture of the Q-spoiling process. We have our pin diode Q-spoiling as well as our FET device Q-spoiling. And so with the pin diode method, if you turn the current bias on, the diode turns on, resulting in your Q-spoiling. And to the left bottom here, if you turn on the FET device, you can also create your Q-spoiling effect here. And you would represent both the diode and the FET device as an R on, okay? Which translates to a blocking impedance, R block. And the smaller R on is, the larger your R block is, which means the better the Q-spoiling circuit is for blocking currents. Now there's a lot of numbers on here, but don't worry, I'll walk you through it. So here are pictures of the actual die for the Cree devices that we were using in our experiments. Now in this chart, okay, we have the GaN FET that have been used in past works for Q-spoiling that we will compare with our devices. Here are the properties for the pin diode. And here are three different devices from Cree that we were looking at: a 25 watt part, a 40 watt part, and a 75 watt part. And we will compare these 5 parts. Okay. Now looking at R on, the GaN FET devices have a much lower R on compared to the pin diode as well as the Cree parts. Now, if you look at C off though, you'll see that their off capacitance is 42, which is several times the off capacitance of the pin diode as well as the Cree devices. But we will focus now on the figure of merit, which is the R on C off product. And comparing them, we can see that the Cree devices outperform the GaN FET device by, a factor of 2-ish. The pin diode does better than the Cree devices as well as GaN FET. However, we want to see if these Cree devices are good enough for our purposes, because they do save 100 milliamps of power compared to the pin diode. Okay, so let's do a quick calculation here, because we need to figure out whether the FET devices in our Q-spoil circuit can even handle the amount of current running through it. And to do that, we can calculate the induced EMF in our coil. Okay, and so the induced voltage is going to be proportional to the size of the coil, the B1 pulse magnitude, as well as our Larmor frequency. And so plugging our numbers in using the coil that we prototyped, 20 microtesla is probably as large as anything you will likely play out with B1 in a huge majority of your pulse sequences. and then Larmor frequency is this is a 1.5 Tesla Larmor frequency. And we calculate that down here that the minimum current that the FET device must be able to handle is 2.13 amps. So here is the IDS and VDS curve for the FET device. You will notice that we need to operate inside this linear safe region. And if, for instance, VDS goes too negative, the drain will drop, the gate will then track the drain, and you could have breakdown in the gate source junction. And we have seen in our initial experiments parts literally blowing up in the scanner because they were unable to handle these massive currents that were going through them. So this is an important calculation. So for our experiments, we actually created a set of coils with different Q spoiling circuits. The first coil that we built had the conventional pin-diode Q spoiling circuit. We also built a passive cross-diode Q spoiling circuit. And for our FET device-based Q spoiling circuit, we actually created two different schematics. The one on the bottom left provides a control voltage of 0 or positive 5 at the FET source. And the one on the bottom right provides a control voltage of 0 volt or negative 5 volt at the FET gate. And this is to give us different options in terms of control voltages depending on what our scanner outputs. Now, an important question you may be wondering is, how much blocking impedance do we actually need? And in this abstract written by Victor Tarasilla, he actually used theory and simulation to find an equation that calculates what blocking impedance is necessary in order to achieve less than 5% B1 distortion. So we actually used this equation, and given the size of our coil, to calculate the minimum impedance we need in order to achieve the B1 distortion we want. And we calculated that for 1.5 Tesla, we required at least 2.3 kiloohms. And at 3 Tesla MRI, we require at least 4.6 kiloohms. And so here's a picture of our PCB fabbed prototype coil. And on the left, you see is a picture of the part which we wire bonded to the PCB. And the reason is the package had nickel in it, which could interfere with the MRI scanner. And here are the dimensions of the coils. And so here's a picture of our phantom setup. We have a saline gel phantom with a permittivity and conductivity to mimic that of humans. And we placed a coil right underneath that gel phantom. And this is a top view of that. So it's pretty simple. So here is a summary of the scan tests that we performed. We performed scans at both 1.5 Tesla as well as 3 Tesla. And for each of these magnetic field strengths, we performed 2 different pulse sequences. And don't worry about what these are. You can have whole courses on them. Just so you know, the first one is a gradient echo SPGR sequence at 60-degree flip angle. And the second one is a fast spin echo, which has very high B1 field and really stresses the parts. And that's why we chose this second pulse sequence. And here are the parameters, TRTE, echo. Again, don't worry about what these are. And so the next thing we did is that for the coils that we built for 1.5 Tesla, we took the Q spoiling circuits and we measured the blocking impedance. Okay, so again, we have from the equation that we mentioned earlier on minimizing B1 distortion to be less than 5%, we have a goal of having at least 2.3 kiloohms of blocking impedance. Now for our conventional pin diode Q spoiling circuit, we achieve 5.4 kiloohms. And these are the Q-spoiling circuit blocking impedances for the 25 watt part, 40 watt part, and the 75 watt part. And as you can see, all of these Q-spoiling circuits surpass this minimum requirement, which is great. The pin diode based Q-spoiling circuit obviously does the best, but it does also take additional power. So if it's good enough, as we engineers say. Now, we also did the measurement for our 3 Tesla MRI coils. So here are the results for measuring the blocking impedance on our 3 Tesla coils. And again, from the equation, our goal in order to achieve less than 5% B1 distortion is at least 4.6 kilo ohms. And as we can see for our FET-based Q-spoiling circuits, as well as the pin diode circuit, all of them surpass this minimum blocking impedance requirement. So we performed our scans using the different methods, and the images look pretty good. And we actually took a look at the SNR values for each of the coils that we built. And as you can see, for each of the pulse sequences, the SNR is actually very similar between the FET-based coils and the pin diode coil. And so I mentioned earlier that we built 2 different FET-based Q-spoiling coils. And in this slide, we're going to show whether there's a difference between our source-controlled FET-based coil and our gate-controlled FET-based Q-spoiling coil. And from looking at schematic 1 and schematic 2, we see that in this particular scan that the SNR difference is almost insignificant. Okay, there's a 0.1 difference in this result, and from this and other results, we basically concluded that there is little difference in SNR performance between these 2 different schematics. And so for our 3 Tesla scans, we only built one of them for a comparison with the other conventional Q-spoiling methods. So here are the results for our 3 Tesla scans using the 3 Tesla coils that we built. And we had a pin diode as well as our FET-based coils for 3 of the different power parts. And again, when looking at the SNR measurements for the GRE sequence as well as the fast spin echo sequence, we see that the SNR quantities are very, very similar to one another. Okay, with GRE sequence, we see less than 0.4 dB, which is very close. And the fast spin echo, we see it's less than 0.5 dB, which is very close. And looking at the images, of course, we can't see any difference. So this is an excellent sign. And the fact that our FET devices are able to work at 3 Tesla is just something new. Okay, it hasn't been done before, as far as we know. Okay, so here are the results of our experiment, and we can see that in this first picture, if the coil unpowered has no Q-spoiling circuit on it, we can actually see these Q-spoiling banding artifacts in our image. This is what a Q-spoiling artifact looks like. Now, if we overlapped our connected coil with a conventional pin diode Q-spoiling coil, because the coil is unpowered, the pin diode is deactivated, and therefore there is no Q-spoiling on this coil either. And so we see the same banding artifact. Now, it's interesting because now if you look at the cross-diode coils, as well as our FET-based Q-spoiling coils, we do not see any Q-spoiling artifacts, okay? And another interesting thing is with our FET-based coils, because as I mentioned earlier, because these HEMT devices are on by default, that means that the coils are Q-spoiling when unpowered. And so that's why you see no sensitivity in the regions above these coils, these FET-based coils. So just a quick summary of our FET-based Q-spoiling work. We have seen from our results that the FET Q-spoiling circuits have comparable SNR with the pin diode-based Q-spoiling coils for both GRE and FSE pulse sequences, which is great. And we also noticed that the FET switch coils, they Q-spoil when they're unpowered or unbiased, which is great for safety reasons. We also note that the FET devices are actually very cheap. They're only $40 to $50 per pop. So it's not like a huge cost, it's not a huge monetary cost for us to use these FET coils. And most importantly, we see that using FET-based Q-spoiling is a very nice low-power alternative to conventional pin-diode Q-spoiling methods, especially in array coils. So hopefully in the future, this technology can be applied to array coils for significant power savings and can be used in future wireless MRI receive coils. So that's pretty much it. Thank you all for listening, and if you have any questions, feel free to spam the comment section. All right, thanks. Bye.